Good morning, everyone. This is Sachin Fiske from Electrical Engineering Department, SND College of Engineering and Research Center. Today, we are going to start a new unit that is Frequency Domain Analysis, Part 1. So, before going to the frequency domain analysis, first, all of you know about the knowledge related to what is frequency domain and how it can be analyzed. Let us see. So frequency domain analysis and Fourier transform are a cornerstone of a signal and system analysis. These ideas are also one of the conceptual pillars within electrical engineering. Among of all the mathematical tools utilized in electrical engineering, frequency domain analysis is arguably the most far-reaching. In fact, these ideas are so important that they are widely used in many fields, not just in electrical engineering, but in practically all the branches of engineering and science, and several across all mathematics. Moving toward the frequency content, the first one is the combining sinusoidals. The most common and familiar example of a frequency content in signal is probably audio signals and music and in particular. Now we are all familiar with high musical notes and low musical notes. The high notes do in fact have higher frequency content than the low notes. But what exactly does this means? The place to start to answer this question is to consider the sinusoidal. Recall that the general expression for sinusoidal at a frequency omega, that is, or frequency f in hertz, is x of t is equal to a into sine of t plus a, or sine of omega t plus a is equal to a sine 2 pi ft plus pi. So when considered as an audio signal, that is x of t indicates the change in the air pressure on our ears as a function of time. What is important here is the time variation of the air pressure from some ambient value rather than the ambient value of the pressure itself. A negative value refers to that amount below the baseline pressure, while a positive amount refers to a pressure higher than the baseline. So x of t being a sinusoidal means that the air pressure on our ear varies periodically above some ambient pressure in a manner indicated by the sinusoid. The sound we hear in this case is called a pure tone, and pure tone often sound artificial rather than the music. The frequency of the sinusoidal determines the pitch of the tone, while the amplitude determines the loudness. It turns out that the phase of the sinusoidal does not affect our perception of the tone, which may not be surprising for a pure tone, but is somewhat surprising when we start containing or combining these sinusoidals. Now we can combine the two sinusoidals by adding the signal in the usual way. For example, x of t is equal to sine of 2 pi t plus sine of 4 pi t is a combination of a sinusoidal with frequency 1 Hz and a sinusoidal with a frequency 2 Hz. Here, the amplitude of each sinusoidal is 1 and the phase of each is 0. A plot of x of t is shown in the following figure. See this figure. The sound created by x of t is the combination of the two pure tones that makes x of t. Unfortunately, as we will discuss in more detail, and the humans can't hear the pure tone that comprise the signal x of t above since the frequency are too low. However, we can make a similar combination with signals at frequency humans can hear. And for example, consider the signal dt is equals to sine 2 pi into 230 into t plus sine of 2 pi into 440 into t is a combination of each of these two sinusoids at a frequency 350 Hz and 440 Hz alone corresponds to a pure tone that can be heard by a normal human ear, and this combination, that is the signal d of t, makes a very familiar sound, namely the dial tone on a standard US telephone line. A plot of d of t is shown in the following figure, and note that in this figure only 200ths of seconds are shown because the frequency are high. If we showed even a whole sound of the seconds, the signal would associate or oscillate to so many times, that is 350 and 440 for a constituent sinusoidal, that not much useful detail would be seen. Although the dial tone is a simple example of a sound that still sounds artificial, by combining more sinusoidal at different frequencies, we can get many other sounds. These musical notes that we find cleansing largely consist of pure tones near the pitch of a musical note, but also contains the other frequencies that gives each instrument its particular qualities. Voice and other natural sounds are also comprised of a number of pure tones. Amazingly, all sounds can be built up out of the pure tones, and likewise all the time signals can be constructed by combining the sinusoidal. Thank you.